Welcome to the Deep Dive, where we take a fascinating subject, unpack a stack of information, and deliver the crucial insights directly to you.
Think of it as your express route to becoming seriously well-informed.
Exactly. And today, we're plunging into the details of something genuinely innovative, AlphaEvolve.
Right. This is a brand new AI coding agent developed by Google DeepMind.
Yeah, we've got our hands on their white paper. It's called AlphaEvolve, the coding agent for scientific and algorithmic discovery. So our goal in this deep dive is really to understand how AlphaEvolve is, pushing the boundaries of automated discovery.
In both science and computational problem solving.
Mm-hmm.
And at its heart, AlphaEvolve basically empowers AI to autonomously evolve code. It uses large language models, LLMs, within this kind of evolutionary framework.
Okay.
And that lets it make direct modifications to algorithms, which are then refined based on, well, automated feedback.
Right. Okay, let's unpack this because this isn't just about tweaking existing code a little bit.
No, not at all.
The really exciting thing here, it seems, is the potential for completely new scientific breakthroughs, new practical solutions.
Exactly. All driven by an AI that can essentially program its own way forward.
Okay, so let's start with the basics then. What is AlphaEvolve and, how does it actually do this stuff?
Well, the core idea is actually quite elegant. Humans, we define the problem we want to solve, and crucially, how we'll measure success.
Mm-hmm.
The criteria,
Well,
right?
that's the what.
That's the what, exactly. Then AlphaEvolve takes over the how. It figures out the solution by automatically evolving algorithms.
Okay, and these candidates of discovery, the paper calls them?
Yeah.
These could be new math concepts or just practical ways to solve things. They're all algorithms.
They're all expressed as algorithms. It's like translating an idea into code that a computer can not only understand, but also, change and improve.
Right, so the evolution part, it's like a loop.
Yeah.
LLMs generate algorithms, critique them, refine them.
It's a continuous loop. Yeah. But here's the really important part. It's not just the AI thinking in a vacuum.
Okay.
No, the whole process is grounded. It actually runs the code it generates.
Ah, okay.
And it automatically evaluates how well that code performs against the criteria we set up at the start.
So that automated feedback is key.
Absolutely vital. It stops the AI from, going down rabbit holes that aren't working.
Yeah.
Keeps it focused.
So it's guided exploration, not just random guessing. And the paper says it can find solutions really different from where it started.
That's a crucial point, yeah. It's not just making tiny improvements. Sometimes the algorithm is the goal, like finding a faster way to do matrix multiplication. Big implications there.
Right.
Other times, the algorithm is more like a tool.
Yeah.
A way to build a specific solution, like figuring out the best way to pack spheres together.
Okay, that makes sense. Now, AlphaEvolve, it didn't just appear out of nowhere, right? It builds on earlier work.
Exactly. It's a really significant step up from a previous Google DeepMind project called FunSearch.
FunSearch, okay. I remember hearing about that.
Yeah, FunSearch was kind of the first step, groundbreaking in its own way. AlphaEvolve is, well, it's much more sophisticated, more capable.
So what are the big differences then? What can AlphaEvolve do that FunSearch couldn't?
Well, quite a lot, actually. FunSearch, it basically evolved single functions, maybe, a few dozen lines of code.
Okay.
AlphaEvolve can handle whole code files, hundreds of lines, potentially. And FunSearch was just Python.
Right, only Python.
AlphaEvolve can work with code in, well, pretty much any language. That's a huge jump in flexibility.
Wow, okay. That's massive. What else?
FunSearch needed problems where you could check the answer really fast, like under 20 minutes. AlphaEvolve, it can handle evaluations that take hours using parallel processing on specialized hardware to manage that.
So more complex problem.
Exactly. And interestingly, it does this using fewer LLM samples, thousands, compared to millions for FunSearch.
How does that work?
It suggests a more efficient, more targeted search, probably because it's using the latest, most advanced LLM's state-of-the-art models.
So fewer resources, but much more power. Sounds like a big leap.
It is. Plus, AlphaEvolve uses richer context, better feedback, and its prompts to the LLMs, and it can optimize for multiple things at once.
Multiple criteria.
Yeah, which really opens up the kinds of solutions it can find, balancing different desirable features.
Okay, so we've got the what and the how broadly. Let's get a bit deeper into the actual process. How does this iterative loop actually work?
Right, so it revolves around a few key parts. First, there's a program database. Think of it as a library storing all the good solutions found so far.
Like it's memory of what's worked.
Exactly. Then you have a prompt sampler,
Hmm.
This thing intelligently picks programs from that database to build really detailed prompts for the LLMs.
So it's saying, okay, these worked before. Can you riff on these ideas?
Precisely. Leveraging past success. Then the LLMs do their thing, the creative generation. They get these prompts and suggest changes to the code.
As diffs, you mentioned.
Yeah, as diffs, like track changes for code, showing exactly what to change.
Okay, clear instructions, and then,
Those diffs get applied, creating new program versions. Then the evaluators step in. These are user-defined bits of code that automatically score the new programs based on the problem's goals.
rigorously testing if the change actually helped.
Right. And if a new program scores well,
Back into the database.
back into the program database, and the cycle continues. Generate, evaluate, refine, over and over.
And you mentioned an input API earlier with comment markers.
Yeah, that's a neat practical touch. You use special comments like #evolve block start and #evolve block end.
Uh-huh.
AlphaEvolve only modifies the code between those markers. The rest of the code provides the context.
So you can point it at just one part of a bigger system. Very practical.
Very. And it's flexible about what it evolves, not just lines of code. It can evolve, raw text, whole functions, complex search algorithms.
Wow.
It can even co-evolve intermediate solutions and the search methods used to find them. It's pretty sophisticated.
It really sounds like the LLMs are the creative engine here.
Oh, absolutely fundamental. The paper mentions using an ensemble, specifically Gemini 2.0 Flash and Pro. They're key for coming up with new diverse ideas.
An ensemble. Why two models?
It's strategic. Gemini Flash is faster, so it generates lots of candidates quickly, kind of explores the space broadly.
Okay.
Gemini Pro is more powerful overall, so it might generate fewer, but potentially higher quality, more complex suggestions.
So speed versus depth, essentially. Using both.
Exactly.
Yeah.
And they communicate these changes using that diff block format you mentioned, that search replace thing.
Got it. Ensures the changes are precise. Okay, so code gets generated, modified. But the evaluation is where the rubber meets the road, right? How does it know if it's actually better?
Precisely. Every new solution is automatically evaluated by a function the user provides. That function basically defines good for that specific problem.
And there are ways to make that evaluation faster or smarter.
Yeah, they have some optional tricks.
Yep.
One is an evaluation cascade. You test first on easy versions of the problem.
Filter out the obvious failures quickly.
Exactly. Only the promising ones move on to the harder, more time-consuming tasks. Saves a lot of computation.
Smart. What else?
Well, they can also use LLM-generated feedback sometimes. Like, if you want a solution to be simple or elegant, which is hard to measure automatically, an LLM can assess that sort of subjective quality and give feedback to guide the search. And, of course, lots of parallel evaluation, testing many things at once.
Speeds things up. And it can optimize for multiple scores at once.
Yes, even if you only really care about one main metric, optimizing for related secondary ones can sometimes lead you to even better solutions for the main goal. It encourages exploring different types of good solutions.
Okay, this sounds incredibly powerful in theory, but let's talk results. What has AlphaEvolve actually achieved? Give us some highlights.
Right, this is where it gets really exciting. The impact is already significant across different areas. Let's start with a really fundamental one. Faster matrix multiplication.
Okay, super important for, well, almost everything computational.
Absolutely. AI training, scientific simulations, graphics, you name it. Small speedups here have huge ripple effects.
So what did AlphaEvolve do?
It basically develops sophisticated new ways to do tensor decomposition, which is the math behind matrix multiplication algorithms. And in quite a few cases, its approaches beat the existing state-of-the-art methods.
It found better algorithms.
Yes, suggesting real potential to speed up tons of computational work.
Any specific standout result?
Oh yeah. For multiplying two 4x4 matrices with complex numbers, AlphaEvolve found an algorithm using only 48 scalar multiplications.
Okay, and the previous best?
Was Strassen's algorithm, which needed 49 multiplications. And that record had stood for 56 years.
56 years, wow.
Yeah. So this is the first improvement on that specific problem in over half a century. Shows it can tackle really well-studied fundamental problems.
That's genuinely stunning, breaking a 56-year-old record. And was that a one-off?
No, the paper lists, I think, 14 different matrix multiplication targets where AlphaEvolve improved on the state-of-the-art.
14.
And importantly, it wasn't just tweaking parameters. It introduced genuinely new ideas into the algorithm design itself. Optimization methods, how things were initialized, the loss functions used. Real algorithmic creativity.
So it's designing new approaches, not just fine-tuning old ones. Amazing. But it wasn't just computer science, right? It tackled pure math problems, too.
Yes, and again, with really impressive results. They applied it to over 50 challenging open problems in math analysis, combinatorics, number theory,
A
geometry,
broad
a
range.
very broad range. And it matched the best-known results from human mathematicians on about 75% of them.
Just matching the best human work is incredible for an AI across so many areas.
It really is. But even better, on roughly 20% of those problems, AlphaEvolve actually beat the state-of-the-art, found new constructions better than anything known before.
That's actual mathematical discovery by an AI. Can you give examples?
Sure, in analysis, it improved bounds on things called autocorrelation inequalities and refined an uncertainty principle. Important foundational stuff. In combinatorics, it found a new upper bound for a famous problem called Erdős's minimum overlap problem. And in geometry, it improved the lower bound for the kissing number problem in 11 dimensions.
Kissing number.
Yeah, how many spheres you can pack around a central one without overlapping. It bumped the known lower bound from 592 to 593 in 11D.
Wow. A concrete improvement.
Plus new results in other packing problems, too. These aren't trivial things. They're hard problems mathematicians work on for years.
And how did it approach these? By evolving search algorithms.
Exactly. Instead of trying to directly build the complex math object, it evolved programs that were really good at searching for those objects, given a time limit, and often starting near the best-known solution.
So it discovered clever search strategies.
Yeah, sometimes quite complex multi-stage strategies that adapted as they went along, automated discovery of search heuristics.
The paper mentions collaborations with mathematicians like Terence Tao.
It does, which really highlights how this can be a tool for top-level researchers. They helped frame the problems, showing that synergy between human expertise and AI capability.
Okay, so huge theoretical wins. But did it do anything practical? Like applied stuff?
Yes, absolutely. They turned it loose on optimizing some of Google's own massive internal systems,
Yeah.
real-world impact,
This has
data center scheduling, huge challenge. AlphaEvolve found a heuristic function for Borg that's Google's cluster manager.
Okay.
The heuristic was simple, surprisingly, but really effective. It resulted in recovering, on average, 0.7% of stranded compute resources across Google's entire fleet.
0.7%. Doesn't sound like much.
At Google's scale, that's massive.
Yeah.
Huge amount of computing power reclaimed, saving costs, improving efficiency.
Good point. Scale matters. And the paper mentioned advantages over other AI approaches here.
Yeah, compared to, say, deep reinforcement learning, the solution AlphaEvolve found was much more interpretable, easier to debug, more predictable.
Which is critical for managing infrastructure like that.
Absolutely critical. You need to understand why it's making the decisions it makes.
Okay, what else within Google?
Well, it actually helped optimize the training for Gemini itself.
The AI models.
Yeah, it optimized something called tiling heuristics for a matrix multiplication kernel used heavily in training Gemini.
Okay.
The result, an average 23% speed up for that kernel and about a 1% reduction in overall Gemini training time. Plus, it found this optimization much faster than previous methods.
So Gemini optimized Gemini's training. That's kind of meta.
It is pretty cool. Yeah.
Yeah.
AI improving its own foundations. It also dipped into hardware design.
Hardware. How?
It optimized a Verilog implementation that's a hardware description language for a key circuit in Google's TPUs, their AI chips.
What'd it do?
It figured out it could remove some unnecessary bits from the design,
Yeah.
a change validated by the actual TPU designers.
Mm,
Shows potential for AI helping optimize hardware early on.
amazing. And one more. Compiler optimization.
Right. It directly optimized the intermediate code generated by the XLA compiler for a specific part of transformer models called a flash attention kernel.
Used in things like language processing.
Exactly. It achieved a 32% speedup in that specific kernel and a 15% speedup in related processing steps. So potential for AI to plug right into the compiler pipeline and boost performance.
So it's really spanning the whole stack from pure math theory to low-level hardware and compiler optimization to massive infrastructure management.
It's incredibly broad. Yeah. Breaking old records, delivering real-world efficiency gains.
You know, the real aha moment for me here is seeing how powerful that combination is. The cutting-edge LLMs, the systematic evolution, and that absolutely crucial automated feedback loop.
That combination really seems to be unlocking a new level of discovery, doesn't it? Things that just weren't really possible before.
Definitely. Now, the paper does mention limitations, right? It's not magic yet.
No, quite right. The big one is the reliance on having those automated evaluation functions. You need a way to automatically score how good a generated solution is.
Which isn't always easy, especially in some scientific areas.
Exactly. Think complex biological simulations or material science. Sometimes evaluating a potential solution requires complex experiments or isn't easily quantifiable by simple code execution.
But they have ideas for the future. How to tackle that?
They do. They suggest exploring ways to use LLMs themselves to provide feedback in those harder-to-evaluate cases. Maybe combining the AI's language understanding with the code execution where possible.
Interesting. Kind of using the AI's judgment when automated scoring falls short.
Potentially, yeah. It could open up even more domains for this kind of automated discovery.
So as AI gets better, not just at following instructions, but actually designing the computational processes, designing the discovery process itself, it really makes you think.
It does.
What kinds of breakthroughs, things we can't even imagine now, might be just around the corner, across, well, everywhere.
It's a profound shift. The implications are potentially vast, suggesting a future where AI becomes a true partner in driving scientific and technological progress.
Yeah.
Really exciting times.